Hello everyone and welcome to GeeksforGeeks. In this tutorial, we are going to see how to count the number of inversions in an array. First of all, let us try to understand what do we mean by an inversion. So an element at index I and element at index j form an inversion if the value of element at index I is greater than the value of element at index j, whereas value of I is smaller than the value of j. For example, in the given sequence 2, 4, 1, 3, 5, there are a total of 3 inversions. Let us look at them one by one. So first of all, we look at the elements 2 and 1 highlighted in red. Here 2 is greater than 1, whereas the index of 2 is smaller than index of 1. So they form an inversion. Similarly, the elements 4 and 1 form an inversion as 4 is greater than 1, whereas the index of 4 is smaller than the index of 1. Finally, we look at the elements 4 and 3. They also form an inversion as 4 is greater than 3, but index of 4 is smaller than the index of 3. In this problem, we basically have to find out the inversion count of the array. Inversion count actually tells us how far or how close the array is from being sorted. So if the array is completely sorted, there will not be any inversions in the array and thus the inversion count will be 0. However, if the array is sorted in reverse order, the inversion count will be the maximum possible inversion count value for any array of that size. First of all, let's look at the simplest method. In this method, we iterate over the array element by element, and for each element, we check the number of smaller elements to the right of the selected element. So you see the method getInversionCount. We first of all initialize inversion count as 0. Then we run a loop from 0 to n minus 1, where n is the total number of elements. Then for each element, we run a loop from the element to its right to element at index n minus 1. Whenever we encounter any element which is smaller than the given element, we increment the inversion count. Finally, we return the inversion count. This method solves the problem in order of n squared time complexity. Now we'll look at the solution in which we will be using enhanced merge sort to count the number of inversions in an array. But firstly, we'll quickly recapitulate the original merge sort algorithm. Merge sort works on divide and conquer paradigm. That is, we must recursively divide the given problem into smaller subproblems until they become simple enough to be solved directly. Then the solutions of the subproblems are combined to give solution to the original problem. Given an array, we first of all divide the array into two halves. Then we call the merge sort on each of those halves, and then we finally merge the two sorted subarrays. Here is the big picture of the enhanced merge sort algorithm. We divide the array recursively into two halves and compute the answer of those two halves. Now suppose we know the number of inversions in the left and right half of the array. Then what kind of inversions are not accounted for in inversion 1 plus inversion 2? Well, the answer is the ones we have to count during the merge step. Therefore, to get the total number of inversions, we need to add the number of inversions in the left subarray, right subarray, and in the merge step. Now the question is, how do we get the number of inversions in the merge operation? To answer that, let I be used for indexing the left subarray and j be used for indexing the right subarray. At any step in the merge, if value of element at index I is greater than value of element at index j, then we know that there are mid minus I inversions. This is because both left and right subarrays are already sorted. So if element at index I is greater than the element at index j, then all the elements in the left subarray with index greater than I will also be greater than the element at index j. Let us try to understand this with the help of an example. So here you have the left and right half of the array. Notice that both of these are already sorted individually. So we start with index I equal to 0 and index j equal to 3, whereas the mid index is 3 because from index 3 the right subarray starts. Also the initial inversion count is set as 0. Now we compare the two highlighted elements. One is smaller than 2, so we move it in the merged array and the inversion count remains 0. Now we compare 3 with 2. As 3 is greater than 2, we'll move the smaller element, that is 2, in the merged array. But before that, we see that we have encountered an inversion. Although the value 3 is greater than the value 2, but the index of element 2 is smaller than the index of 3. We already know that first subarray is sorted, so elements coming after 3 will be greater than 3 and thus will also be greater than the value 2. So they all form pair of inversions with the element 2. So in total, we see that there are mid-index minus I, that is 3 minus 1 equal to 2 inversions in this step. So we'll increment the value of the inversion count by 2. Now we compare 3 with 4. As 3 is smaller than 4, we move the value 3 to the sorted array and increment the value of I. Now we compare 5 with 4. Clearly 5 is greater than 4, but the index of 5 is smaller than the index of 4. So we have again found an inversion. As per our algorithm, we'll add mid index minus I, that is 3 minus 2 equal to 1 inversion in the inversion count. After that, we'll move 4 into the sorted array and increment the value of j. Now we compare 5 with 6. As 5 is smaller than 6, we move the value 5 to the sorted array. Now as all the elements of the left subarray are already processed, we'll just move the remaining elements of the right subarray to the sorted array. After all the elements are processed and moved to the sorted merged array, we have the inversion count of the merge step as 3. Now let's understand the algorithm better with the help of its implementation. So the implementation starts with the merge sort function, which takes as an argument the array and its size. Inside this function, we create a temporary array and pass it to underscore merge sort method along with the original array. We also pass the starting index and ending index of the array, that is 0 and array size minus 1 respectively. Now let's see the underscore merge sort method. Here we declare the variables mid and inversion count. We also initialize the inversion count with value 0. Here we check if the right is greater than left, then we do the following. We calculate the value of mid as right plus left divided by 2. Now as per the algorithm, we call the underscore merge sort method for the left subarray and right subarray. Notice that the left subarray is from left to mid index, whereas the right subarray is from mid plus 1 to right. We add the inversion counts returned by these two respective calls to inversion count variable. Finally, we call the merge method to merge the left and right subarrays and add the inversion count returned by the underscore merge method to inversion count variable. Lastly, we return the value of inversion count. In merge method, we first of all declare variables I, j and k. Then we declare inversion count and initialize it as 0. Then we initialize variables I as left, j as mid and k as left. Then while either one of the array is not completely processed, we do the following. We compare the elements at index I with element at index j. If element at index I is smaller than or equal to element at index j, then we just copy the element at index I to the temp array and increment the values of k and I. Otherwise, We copy the value at index j to the temp array and increment the value of both k and j. Additionally, as per the algorithm which we just discussed, we encounter the inversions in this case. So we add mid minus I inversions to inversion count. Once this is done, we copy the remaining elements of the left subarray, if any, to the temp array. Then similarly, we copy the remaining elements of the right subarray, if any, to the temp array. Finally, copy the values from the temp array back to the original array and return the inversion count value. Now coming to the time complexity, the time complexity of this solution is same as that of merge sort algorithm, that is order of n log n, and the algorithmic paradigm used is divide and conquer. So in total, we discussed two methods to solve the problem. The first one was simple method which solves the problem in order of n squared time complexity, whereas the second method used enhanced merge sort solved the problem in order of n log n time complexity. So that is all for this tutorial. Thank you.